Materials and structures in aerospace often have to operate at many different temperatures, ranging from high to low and for a long time. For instance, in space it's pretty cold. In outer space the temperature reaches -270 degrees Celsius. Closer to Earth, it depends on whether an object is in the sun or in the shade, with temperatures varying from 120 degrees Celsius to -100 degrees Celsius. Aircraft also have to operate in temperatures ranging from -50 degrees Celsius and up to +50 degrees Celsius. If we take a look at component level, in an aircraft engine, extremely high temperatures can also be endured, reaching up to 1400 degrees Celsius. Finally, when space vehicles re-enter the Earth's atmosphere, the highest temperatures are reached. The Space Shuttle endured temperatures of about 1650 degrees Celsius. This means that selecting or designing the right structures and materials for the job is essential in order for aircraft and spacecraft to operate. What happens to material properties if a material is subjected to a change in temperature? If we look at this graph, which shows the variations in ultimate and yield stress of aircraft-grade aluminum as a function of temperature, you can see that the ultimate and yield stress become lower as the temperature increases, both rapidly degrading after 135 degrees Celsius, which is why this temperature has been set as the nominal maximum operating temperature. Also, parameters such as elasticity and elongation are dependent on temperature for metals. Although most engineering materials are affected by temperature, it is important to highlight polymers here, such as those used to create laminates. They may experience a transition in their material response, even though the temperature is not at its melting point. What happens is that a polymer goes from a solid state into a rubbery state. This transition point is called the glass transition temperature. As this greatly affects the modulus of elasticity, as can be seen from the graph, polymers are never used above the glass transition temperature. In general, the higher the temperature, the more the mechanical properties of a material deteriorate. What you can see happening is creep, where the material undergoes steady, ongoing deformation under application of constant stress. Also, a low yield strength and more plastic, hence permanent deformation occurs. Both of these phenomena can really affect operations and are therefore limiting factors when selecting materials that have to endure long exposure to high temperatures, such as the turboblades in an aero engine and the thermal protective layer of reusable spacecraft during re-entry. Next to the effect of the environmental temperature on the mechanical properties, designers must also take into account thermal stress. This is caused by materials expanding or contracting due to the change in temperature. The relation between the temperature and the volume is described by the thermal expansion coefficient denoted by the lowercase Greek letter alpha. It is equal to 1 over the volume V times the change in volume with the temperature, dV over dt. The thermal strain is then equal to the thermal expansion coefficient alpha times the change in temperature delta T. From this, you can now calculate the thermal stress. In summary, we can now say that higher temperatures have a negative effect on the mechanical properties and the fatigue properties, and increase the thermal stresses. Fatigue is the phenomenon of damage caused by multiple load cycles below ultimate strengths, resulting in less load-bearing capability of a structure. Think of a paperclip that you fold and unfold. Vice versa, at low temperatures, the mechanical properties improve, as do the fatigue properties, as can be seen in the graph. Also, the resistance against plastic deformation goes up. As it is colder, many chemical reactions slow down or don't occur. A famous low temperature case, where the designers did not take the effects of temperature into account, is that of the US-built Liberty ships and T2 tankers. They were designed to provide reinforcements for the war efforts during World War II and were built in under 5 days. They broke into two while still in their dock. Investigations showed that the steel used was very sensitive to low temperatures, with a significant transition in fracture and impact toughness, leading to this type of brittle failure. So in short, temperature affects material properties and can also result in thermal stress being present in the structure. Being aware of ambient and operating temperatures is therefore vital as a designer.